A single quart, picked up at any hardware store. No contractor, no permit, no $4,000 epoxy system. And yet, the concrete industry has never once put this solution on a product label. Not in 2021, when Texas homeowners watched their garage floors crack and crumble in 18-degree freeze cycles. Not in the 1960s, when a university chemist documented exactly what happens inside a concrete pour when water freezes. Not today, when that same $3 solution sits on a shelf 2 aisles away from the $89 waterproofing membrane that doesn't work. The chemistry is real. The history is over 1,000 years old. The reason you've never been told about it, that is just economics. Welcome to Hidden Fix Lab. This channel exists for one reason, to hand you the information that billion-dollar industries spent decades keeping off the label. Now, before we go further, if you are new here and someone shared this video with you, do us a small favor. Hit that subscribe button. Think of it like this. Your grandfather never threw away a tool that still worked. Don't throw away a channel that still tells the truth. Subscribe and keep it in your toolbox. And while you are here, drop a comment below. Where are you watching from today? Whether you are in Texas, Toronto, Karachi, or a small town nobody has heard of, we want to know, because this problem does not care about your zip code. Now, let's get into what they never put on the label. Most people assume waterproofing is a modern invention. They picture chemical labs, patent filings, billion-dollar R&D budgets. They assume that if a solution this simple existed, someone would have told them by now. They are wrong. The story begins not in a laboratory, not in a hardware store. It begins in the deserts of North Africa, roughly 700 AD, where Islamic engineers were solving a problem that would not be officially discovered for another 13 centuries. They were building cisterns, underground water storage chambers carved from stone and lined with a material they called al-qadad, a mixture of lime, volcanic ash, and water. These cisterns held drinking water for entire cities. They did not crack, they did not leak. Some of them still stand today. That is just economics. Build it right once, never build it again. But the story goes even further back. Roman engineers, working between 300 BC and 400 AD, used a nearly identical compound to waterproof their aqueducts, harbor walls, and bath complexes. They called it opus signatum. It was lime-based, it was cheap, and it hardened over time rather than degrading, a behavior that puzzled scientists for decades. The Pantheon in Rome still stands after 2,000 years. The harbor at Caesarea Maritima, built by Herod the Great using Roman volcanic lime, has been underwater for 20 centuries and has not dissolved. Modern concrete begins cracking in 15 years. Nobody connected these dots for a long time. Then, in 2017, a material scientist named Marie Jackson, working at the University of California, Berkeley, published a study in the journal American Mineralogist. She and her team had drilled into ancient Roman marine concrete pulled from harbor sites across the Mediterranean. What they found stopped the engineering community cold. The Roman concrete was not just surviving underwater, it was getting stronger. The seawater was triggering a slow chemical reaction inside the material, growing interlocking crystals of a mineral called tobermarite directly into the pore spaces of the concrete. The pores were being filled from the inside, not sealed from the outside, filled from the inside. This was not waterproofing in the way the industry defines it today. This was densification, a process where the material itself becomes the barrier, not a membrane sitting on top of it, waiting to peel. Jackson's team traced the mechanism to one compound, lime, specifically pozzolanic lime, a form of lime that reacts with silica in the presence of water to produce calcium silicate hydrate, the same compound abbreviated in materials science as CSH, the same compound found in every bag of Portland cement sold in every hardware store in America for $3 a quart. The discovery was published, the findings were peer-reviewed, the journals reported it, and the waterproofing industry said nothing. Not one product label changed, not one contractor certification updated, not one home improvement chain moved the $3 lime solution to the waterproofing aisle. That is just economics. The water does not attack concrete from the outside. Most people never hear that sentence. They are sold membranes, sealers, epoxy kits, all designed to stop water at the surface. But the surface is not where concrete dies. Concrete is not solid. Under a microscope, it looks more like a sponge than a stone. Millions of microscopic pores run through every slab, form naturally as water evaporates during the curing process. These pores are the problem. When water enters them, and it always enters them, it sits inside the slab. In cold climates, that water freezes. Frozen water expands by exactly 9%. That 9% expansion pushes against pore walls with pressures exceeding 2,000 pounds per square inch. The concrete does not crack because it is weak. It cracks because it is full of water it was never designed to release. In 2021, Texas recorded temperatures of 18 degrees. Millions of concrete floors, garage slabs, driveways, basement floors, cracked within 72 hours. Homeowners blamed the cold, engineers blamed poor construction. Neither group mentioned the pores. A 2006 study published in Cement and Concrete Research by researchers Mehta and Montero documented exactly this mechanism. They called it the freeze-thaw cycle, and they measured the cumulative internal damage it produces across just 20 winters. By year 20, an untreated concrete slab had lost an average of 30% of its load-bearing integrity, not from surface wear. From internal expansion, repeated season after season invisible to the eye, this is where the $3 solution enters the chemistry. When hydrated lime, calcium hydroxide, is introduced into a concrete surface, it does not sit on top. It migrates inward through the same pore network that water uses. Once inside, it reacts with silica compounds already present in the concrete matrix. This reaction produces calcium silicate hydrate, CSH. CSH does not coat the pore, it grows inside it, crystal by crystal, slowly filling the void that water previously occupied. A 2013 study published in the Journal of Materials and Civil Engineering measured the result. Treated slabs showed a 12% increase in surface hardness. Pore volume reduced by measurable percentage points. Water absorption rate dropped, not because a barrier was added, but because there was simply less space for water to enter. The pore was not sealed, it was eliminated. That is the difference the industry never explains. That is just economics. In 1962, a chemist named Raymond Rowe submitted a report. It was not dramatic. It was not a protest. It was a quiet, technical document submitted to the Portland Cement Association, outlining exactly how hydrated lime, applied directly to cured concrete, could eliminate internal pore volume and permanently reduce water absorption. Rowe was not an activist. He was one of their own. They filed the report, and they never acted on it. That is just economics. By 1962, the waterproofing membrane market in the United States was already generating over $400 million annually. Contractors depended on it. Supply chains were built around it. Certification programs trained around it. A $3 per quart lime solution that homeowners could apply themselves in a single afternoon did not fit that model. It was not suppressed through secrecy. It was suppressed through silence. Nobody banned the information. They simply never repeated it. The Portland Cement Association, founded in 1916 and still operating today, has published thousands of technical bulletins over its history. Bulletins covering admixtures, curing agents, sealers, epoxy systems, and polymer coatings. Raymond Rowe's 1962 findings have never appeared in a consumer-facing publication, not once. The association's primary funding comes from cement and concrete product manufacturers, companies whose revenue depends on repeat application products, not permanent single-coat solutions. That is just economics. The epoxy flooring industry alone reached $2.8 billion in global market value by 2022. The waterproofing membrane segment, products applied over concrete rather than into it, was valued at $14.6 billion globally in 2023. Every product in that $14.6 billion market sits on top of the concrete. None of them address the pore. None of them stop the freeze-thaw cycle from continuing inside the slab. They delay visible damage. They do not stop internal damage. And when they peel, which epoxy systems do reliably within 5 to 7 years on floors subjected to temperature fluctuation, the homeowner buys again. A customer who buys once is not a business model. A customer who buys every 5 years is. In 2019, a materials engineer named Dr. Paulo Montero, the same Montero who co-authored the 2006 freeze-thaw study, gave a lecture at UC Berkeley publicly stating that Roman concrete outperformed modern waterproofing systems on every measurable durability metric. The lecture was recorded. It is publicly available. No waterproofing manufacturer responded. No trade publication ran the story. No home improvement retailer changed a single shelf label. The $3 lime solution remained 2 aisles away from the $89 membrane kit, exactly where it has always been. This is the part the industry hoped you would never reach. Not because the method is complicated, because it is not. Because once a homeowner understands it, really understands it, they never need to buy a waterproofing membrane again. The compound is hydrated lime, also sold as calcium hydroxide, slaked lime, or type S lime. Available at every hardware store, masonry supplier, and farm co-op in the United States. Average retail price, $3 to $4 per quart. 1 quart treats approximately 50 square feet of concrete floor. A standard 2-car garage runs 400 square feet. Total material cost, under $32. Surface preparation. The concrete must be clean, dry, and free of existing sealers or epoxy coatings. If a previous coating exists, strip it completely. A coating on top of lime does not fail slowly, it fails suddenly. Sweep the floor. Remove all dust, oil, and debris. If oil stains are present, scrub with a trisodium phosphate solution and rinse thoroughly. Allow the surface to dry for a minimum of 24 hours before application. Mix and combine 1 part hydrated lime with 4 parts clean water. Stir until fully dissolved. No lumps, no sediment at the bottom. The mixture should have the consistency of thin milk. Do not thicken it. Thin penetrates. Thick sits on the surface and flakes. This distinction matters. A thick mixture behaves like a surface coating. A thin mixture behaves like a migration agent, carrying lime deep into the pore network where the CSH reaction occurs. Application. Apply with a wide masonry brush or a low-pressure garden sprayer. Work in small sections, 10 square feet at a time. Do not allow pooling. If pooling occurs, spread immediately with the brush. Allow the first coat to absorb fully, approximately 20 minutes in normal conditions. Apply a second coat immediately after absorption. Do not wait for the surface to dry completely between coats. The pores are open and drawing inward. That window is the application window. Total application time for a 2-car garage, under 2 hours. The user story. In the winter of 2022, a retired school teacher named Gerald Hoffman in Amarillo, Texas, applied this exact method to his garage floor, a slab that had developed visible freeze-thaw cracking after the 2021 storm event. He spent $28 in materials. He applied the solution on a Saturday morning. 2 winters later, his floor showed 0 new cracking, 0 spalling, 0 surface separation. His neighbor spent $400 on an epoxy system that same spring. By 2024, it had begun to peel at the expansion joints. The final number, industry waterproofing solution. $89 to $1,400 per application. Reapplication cycle every 5 to 7 years. Lifetime cost on 1 garage floor over 30 years, up to $8,400. Hydrated lime, $28 total. 1 application. No reapplication cycle. The information was always available. The chemistry was always real. The price was always $3. They just never put it on the label. That is just economics.